Hello everyone, welcome to this video. This is the second part of GET102, Engineering Graphics and Solid Modeling 1. Sorry that this is coming late. I should have done this a lot earlier. I had quite a lot on my hands. So this video is going to be uploaded to YouTube and you can have access to it. I will keep it up there for the length of time that you're going to do your exams, and then I'll take it down to allow me to record it properly and possibly put them in a series before I keep them permanently up for use. So in this course we will look at introduction to design thinking, introduction to engineering graphics, orthographic projections. Now I do understand that some of these Mr. Kwasame may have already handled them with you, but I'll still go over them. The major thing we would have loved, or we will do, is to just give you a basic introduction to the use of Vision 360, which is one of many very, very good 3D modeling softwares that are out there. So we'll look at design thinking very quickly, just introductory parts to it, introduction to engineering graphics, orthographic projections, sketching, section views, and then we'll come to the use of Vision 360. Now, each of these topics, we will just give you just introductory coverage of them as you progress in your course. We will handle in-depth coverage of this much later. So let's look at the introduction to design thinking. What is design thinking? Design thinking is a methodology. Okay, it's a way of doing something, right? That something is the development, the generation of solutions, innovative solutions to human-centered problems. So if we would define it, design thinking is an iterative, human-centered problem-solving methodology. Okay, and this methodology employs creativity and the use of engineering sciences in the development of innovative solutions to problems. Okay, it's a process, it's a way, it's an approach to handling the problems that we see around us. So what is the design thinking process? Now there could be many different sort of models of the design thinking process, but their skeleton is basically the same, right? So the first stage, or the first thing you do in the design thinking process, is to identify a problem and to empathize. Okay, and then you research that problem, then you define it properly so that it guides your ideation process, it guides your problem solution generation process. So you identify a problem, you empathize, you understand the problem properly, you put yourself in the shoes of those who are facing that problem, and then of course that helps you to understand the problem better, to understand all the nuances around it, to recognize things that you may not have recognized from an outward looking point of view. Okay, and then you go ahead and you do research. You check what has been done previously regarding that. You look around the principles and scientific concepts that govern some of the occurrences in and around the problem. So when you do that research to look at all the theories involved in that problem, and what people have done before in attempting to solve that problem, how they were successful, um, what they couldn't be successful with, and all of that, then you can now sit down and define properly the aim of your design thinking process, right? So, what exactly are you setting out to achieve? What are you hoping to solve? Um, After the research and define stage, then you ideate. Ideate or ideation is the stage where you generate ideas. Okay, like the name implies, you ideate. You generate different ideas on how this problem that you've just defined can be solved. Okay, usually there are two major stages in the ideation stage. There is the concept generation stage, and then there is the concept selection stage. In the concept generation stage, your focus, your aim is to generate as many plausible ideas as you can. Okay, not minding whether they are really sensible or not, whether they will work effectively or not. The goal is just to generate as many ideas as possible, right? Now, when you generate those ideas, then you begin to evaluate, you begin to analyze, all the solutions that you generated to see so which one will solve the problem best, which one is the best and most effective solution, given or taking into consideration costs, taking into consideration power usage, taking into consideration waste generation, and all of that. Okay. When you now ideate, the next stage is where you do design calculations and simulations. So you go about sizing the components, sizing the various features and various aspects of your solution. So if your solution is a given machine, you would want to determine the sizes of all the various parts of the machine that will allow that machine to perform its function without failure. Okay, so when it's put in use, all the forces acting, all the conditions under which that machine will operate, you want to check and ensure that the machine is adequately sized, the materials are selected appropriately to ensure that it functions properly without failure. Okay, you can have a very wonderful solution and poorly select the sizing of various components, and your machine fails in use, or you select materials that cannot withstand the operational conditions for your solution. So the design, calculations, and simulation stage is where you apply a lot of the engineering sciences, you apply a lot of the equations and the mathematical models that have been generated over time for sizing various aspects. You could be dealing with shafts, you could just be dealing with the thicknesses of sheet metal. You might be dealing with bearings, you might be dealing with even fasteners and all of that. What size of shaft should you use if you want to transmit this amount of power and all of that. Further down the line, you will be taught how to go about these design calculations and even how to run some of these simulations. Now, when you have determined component sizes, feature sizes, sizes of various aspects of your solution, then the next thing is to create or to go ahead and build a physical prototype. Okay, a physical prototype of your solution. So using all the sizing and calculations you've done, you go ahead and fabricate. You go ahead and source or pick from the shelf various components and assemble them into your solution, into your machine if it were one. Okay, for the purpose of testing, to now see if your simulations were right, then this machine should behave or should function without failure. Okay, it also gives you an opportunity to measure things like efficiency and the rest of them. And that is the last stage in the design thinking process, where you test this product, this solution that you have just generated. So that's the design thinking process. It starts with you identifying a problem and empathizing around it. Then you move to the research and definition stage. And then you move to the ideation stage. And then you carry out design calculations and simulations to determine sizes and sizing of various components and features. And then you build the physical prototype upon which you run various tests to evaluate if your solution is actually an effective solution to the problem that you initially identified. All right, so let's quickly now move on to engineering graphics. Now, if I would come back a bit, somewhere in this process between the design calculations and simulation stage and the prototype stage, you will need to produce a way of communicating your solution and the sizing of it. Okay, that's what you've already begun to learn how to do, drawing or doing engineering graphics. Okay, so in this design process, you'll do a lot of sketching. We'll look at that a little bit better, which helps you to put your idea on paper. Okay, it gives form to it. It helps represent what you're thinking in your mind. And then when you would have done your design calculations and simulations, you go ahead and draw graphical representations of the idea that you have, so that anybody that looks at it, they say that a picture is worth 1,000 words. Once they look at it, they do understand exactly what you're thinking of. And when you put dimensions and all of that, as we find in a working drawing, then anybody anywhere can pick that up and produce that given component, as it were. So let's quickly look at engineering graphics. What is engineering graphics? Engineering graphics is the creation of visual representations, all right, or visual models of objects, components, it could be systems, all right, and you use the mathematical rules of projection. Okay, so when we create visual representations of objects, of components, or even systems, okay, all in accordance with some rules, okay, which you already begun to learn over time in the last few weeks or so, then you are dealing with engineering graphics. And this is the fundamental language that engineers use in communicating their ideas and their concepts. Now, the information that engineering graphics convey, one, the design intent. Okay, so you've thought up a solution, you've thought up a product that is meant to be the answer to a given problem, right? When you draw, or when you use engineering graphics as a communication or a language, you first of all are conveying your intent. What is the intended shape of your product? What should be its size? How big or small is it? Okay, and what are the functions of all the various components or the assembly, of a few components that you've generated. So first, the first information that engineering graphics conveys is design intent. And then it also conveys manufacturing instructions, okay? What you majorly do in and around your engineering graphics that we're doing now is basically, conveying design intent, looking at the intended shape or the intended form of your product, the size, and then the function of the components, okay? And sometimes even how this should be assembled, as we will look at the third point, right? But in addition to that, engineering graphics also does outline the steps, and the processes that are required to produce each of the components or the product, or the assembly, the components in a given assembly. Okay, so what are the processes? How do you go about producing this component? What steps should you follow? All of that can also be included in engineering graphics. And then you also convey assembly instructions, the sequence. Okay, what do you how do you put this machine together? You have a machine that may be made up of maybe a few hundred components. Okay, which component goes into what? Okay, and how do you assemble them together? How do you fasten them? Which face flushes with which, and all of that. Okay, and we usually use an exploded view. Okay, something we call exploded view, where you take an assembly and you sort of explode it such that every component is orientated in the way in which it should be fitted together, so you know what goes into what. We'll look at a few of these more practically later. So what are the methods of achieving engineering graphics? First is manual drafting, okay, which has been in use for decades and decades and decades, right? And it involves using paper, pencils, pens, rulers, compasses, set squares, and all the drawing instruments that you have in generating these visual representation of the idea that you have, okay? And this is where Mr. Kwasambe first came handled. So you have your drawing board, you have your drawing sheets, your T-squares, and all of that, and then he's showing you methods, ways, how do you show the development of a frustrum of a cone, for example, right? And then you learn the processes of doing that. That's called manual drafting. Okay, and then the second method of generating engineering graphics is computer-aided design, what is generally referred to as CAD, commonly referred to as CAD, which is the acronym for computer-aided design, right? And this is when we use computer software, okay, instead of our own hands and all the instruments that we have. We use the computer software to create 2D profiles and 3D models, okay? And then many times from those models to generate working drawings from them. And then we could take the solid three-dimensional models and perform analysis and simulations on them to sort of figure out or observe how they may behave in real life, given certain loads and given certain boundary conditions and certain constraints. Okay. All right. So this is just an image that shows someone doing a manual drafting. Okay, you can see his sets of instruments all around the table. You can see a ruler, pencils, compasses, sharpeners, erasers, and the rest. And then here's an image of someone who is using a computer to generate visual three-dimensional representations of a system. Now let's go on to talk about how critical engineering graphics is, particularly to the engineering profession. One is that it provides very clear communication, right? It provides an unambiguous and a very precise way of conveying complex technical information. If you were to describe a system, you can imagine this system of gases and pipes and all of that this young man is working on. If you were to use words to describe each and every one of these, you know how very lengthy and very difficult that will be. But with engineering graphics, it's very, very easy to convey very complex technical information without ambiguity and in a very precise way. So it offers us very clear communication. That's why engineering graphics is very critical in the engineering profession. A second is design visualization. It enables us to see, to be able to visualize what a design will look like before physically building it. All right, what would it look like, and also, to enable us to analyze a few things, either of its form, its shape, or how it behaves under load and all of that. Okay, and then engineering graphics are very, very critical and important because they aid manufacturing accuracy. They ensure manufacturing accuracy. Okay, so with them, you are sure that the components and the products that you have envisioned, that you have ideated, that you have conceptualized, are produced the exact way you have. If you have to write to describe, or if possible, even use an audio recording to describe what you want, maybe a machine shop engineer to fabricate for you. There are so many points at which ambiguity could arise. Okay, there could be misunderstanding. If the machine shop engineer does not understand certain terminologies that you are using, then a very different product comes to you at the end of the day. So it ensures that components and products are manufactured accurately and to the correct specifications. It also ensures quality control, right? It ensures that the products you're thinking about are of the quality that is desired, okay? And that is because you're able to, if you have inspectors, if you have people who are coming to check the products that are being manufactured, there is a reference point, which is your engineering graphics output, a drawing, a model, or something like, okay, this is the original concept. This doesn't look like this. It's deviated from. So if someone comes and let's assume that you are very basically, you are fabricating steel pipes, right? They're able to check the thickness of the pipes and the diameter of the pipes with respect to, okay, the graphics that have been produced. Okay, because engineering graphics will convey the intended shape, the intended size. Okay, so it's saying this should be of thickness 0.5 millimeters. The diameter should be about 10 millimeters, thereabouts, right? When you pick your vernier caliper and you're measuring, there is a reference point that aids your inspection, and then that drives quality control. And finally, it aids in problem solving. Okay, so when you ideate and think about something, you may not at that point be able to identify problems, maybe with the form, maybe with how you expected that it would work. But when you have engineering graphics, particularly when you come to computer-aided design, and you're able to generate three-dimensional models of your concept, then it becomes very clear where problems lie. And you're like, oh, I didn't think about that. Oh, wow, I didn't know that this was going to interact with this in this way. So it aids in problem solving by helping you to identify problems and potential issues very early, even before you go ahead and build the physical product. So let's quickly jump to sketching. Now, sketching involves the creation of visual representations of objects. Of course, you're using lines, you're using curves, but the lines and the curves that you're going to use will be drawn with freehand or by using a ruler, okay? Usually not to scale. So when you sketch, you can pick a pencil, you can pick a pen, and just with your free hand, you can create a visual representation of an object or something that you are thinking in your mind or something that you're seeing physically, right? Or you could use just your pencil and a ruler to ensure straightness of lines and all of that. But what you're drawing, you are not drawing to scale. That's what we call sketching. Okay, and there are various tools that are needed for sketching. Okay, you certainly need a pencil or a pen. You need sketchbooks. You can still sketch, on electronic tabs, which use stylus pens and the rest in place of physical pencils and pens, right? There are erasers, rulers, templates, and all of that. Now, templates, when we're in secondary school, even now, when you buy the basic mathematical set that we have, there are some templates inside that have alphabets, A, B, C, D, and all of that, numbers and a few shapes. That's what we call a template, where you can place down and write out text and a few shapes, as it were. Now, sketching is a skill. It's a skill and it can be developed, okay? The basic thing you use for sketching, like we said earlier in our definition, are lines and curves. Lines and curves, okay? People who sketch well, now if you look at these two images that we've got here, they're all sketches. They look really artistic and really beautiful, okay? The one with lines, you see that every shape there is made by straight lines, relatively straight lines, okay? And it's just amazing to see that some of these lines, most if not all of them, are drawn with freehand, okay? So when you want to be good at sketching, you must perfect, okay? There are techniques that you use. You must perfect your ability to draw lines that are straight, okay? And there's a lot of repetition that goes on in ensuring that straight lines are drawn, okay? And the same thing with ellipses, circles, and all of that. You are able to perfect your ability to draw them, okay? So these are forms that you must perfect if you would sketch well. Now, when you sketch on a paper or on a screen that is basically two-dimensional. It's flat, okay? And when you want to represent depth, there are a few techniques that can be used to represent depth. And, when you start talking about depth, we're saying, how do you show that an object is three-dimensional on a two-dimensional sheet of paper or on a two-dimensional screen, okay? Now, the first technique is hatching, okay? Hatching, where several dense lines are drawn very close to each other, okay? The darker parts of your three-dimensional shape, that depending on where your light source will be from, you have denser lines, okay? The very first image that we see there is the case of using the hatching technique to add depth. So you can see that that's not just a circle. Once you look at that, you know that it's a ball. It's a solid ball. It's a sphere, okay? And then there's also cross-hatching. Hatching and cross-hatching actually go together. For hatching, all your dense lines are in a given direction, right? The same direction. In cross-hatching, you have a set of lines that cross each other at an angle, usually 90 degrees, could be any angle at all, okay? So you first hatch and then you cross-hatch. You draw other dense lines, not necessarily perpendicular, at an angle to the first sets of lines that you've drawn, okay? And then there is also the stippling. Stippling is more like dotting, okay, where you're creating dots, several dots, and you make a given region denser than others, and that's how you add depth to that. Okay, and then there's scribbling. Scribbling is a technique where you without taking off your pencil from your pen or from your paper, you go ahead and scribble. Okay, you do continuous circles, continuous lines going over themselves as you move around on your board to show that. Then circling is quite like stippling, but you draw very tiny circles with your pencil, okay, or your pen, as the case may be. That's circling. The smooth shading, you incline your pencil or your pen at an angle and you run it over, okay, several times, back and forth, to shade. We've all known how to shade at some points in our educational journeys. Great. Now let's move on to orthographic projections, okay? And orthographic means at 90 degrees too, okay? So when we talk about orthographic projections, we are referring to a method, a way of creating a two-dimensional drawing that represents a three-dimensional object. Okay. Now we've just seen techniques that can be used to add depth, okay, to a drawing to show that it is three-dimensional. Now in orthographic projections, we look at different faces, okay, different viewpoints of that object, and draw what we see, the two-dimensional form or profile that we see. Okay. And when you have 2 or 3 of such profiles, it's very easy to imagine or to generate what the three-dimensional object represented by the two-dimensional drawing is. Okay, and so the basic principle is that we project that object onto planes that are at right angle to the plane of projection. Okay, now what that means, before I explain that, let's first of all talk about the quadrant system so that when I get back to explaining that you understand. So you will shortly get to know that, there are 2 major ways or techniques for orthographic projections, or 2 major types. The first type is what we call the first angle projection, and then the second one is what we call the third angle projection. Now imagine 2 planes, okay, that meet at right angles the way the screen, the slide is showing. Okay, the horizontal plane is called the X plane on the horizontal plane, and then you have a vertical plane called the Y plane on the vertical plane. Now, these 2 planes, as it were, divide the space, the volume they are into 4 regions. Okay. And we can see the first quadrant, we can see the second quadrant, we can see the third quadrant, and the fourth quadrant has been shown. So when you want to create an orthographic projection, you place your object in one of these quadrants. Okay. Now for the first angle projection, you place the object that you're dealing with in the first quadrant, right? Okay, and that's what you're seeing. And then you project. Okay, a projection will mean you draw lines, okay, in line with edges and in line with vertices, okay, the corners of your shape. All right, so you can see that from various directions or viewpoints, this object that I've placed in the first quadrant have been projected, okay, and they are projected to a plane that is at 90 degrees to your projection. So if you're going to draw a line, that line should meet, okay, I don't know whether you would see my cursor here now. If you can see my cursor, that's fine. If not, it's all right. So you can draw in projection. You want to follow this line, okay, until it gets to that plane. Now the line that you're going to draw in projecting this line or this vertex to that point will have to meet that plane at 90 degrees. Okay, that's what we're talking about. So how do you view this? This for first angle projection. You can see where this young lad is standing, and you can see his line of sight. All right, when he looks at that object from the viewpoint or from the stance point where he has taken, what will he see? Assuming that he stands in such a way that the object is directly in his line of sight. Okay, or what he sees, he projects that onto the plane behind the object. Okay, and we can move his position to this other side, where again he looks along the line of his sight at the object placed in the line of his sight, and that whatever he sees is projected to the plane behind the object. So in first angle projection, in first angle orthographic projection, the object is placed in the first quadrant, okay, and then the views of the objects are projected onto the principal planes as we identified earlier. Okay. So for that given object, these are the things that you would see. All right, the front, that's what we call the front, that's what you call the side elevations, right and then the left elevations, and then you have the plan, which is you viewing this object from the top. And when we get to Fusion 360, we will deal with a few models to show you what the first angle projection will look like when you look at them. Okay, so there are the descriptions: the front view, the right side view, the left side view. Now, for the first angle projection, note that what you see, all right, on the right side of the object is projected to a plane on the left, and what you see on the left side of the object is projected to a plane on the right. Okay, so if we come back here, you look at this young man standing here. His left, all right, is this face that is facing us, as it were. We're looking at our screens, right? Now, if this young man should move from this point to this edge and view this, okay, this image that he's seen, that profile, will need to be projected onto that plane. Now, if we open this plane up, it's going to appear on the right side, okay, on the right side of the drawing, even though it is a representation of the left side of the object, okay. And so for first angle projection, your left view of the object is drawn on the right side of the projection drawing, and then the right side of the object is drawn on the left side of the projection drawing. And then the plan that you would see by looking at the top, on the top of your object, is placed beneath, under the front view. Okay, these two symbols here are the symbols for drawing, or the symbols for that indicate that a given drawing is in first angle projection. Note that the circle is placed at the bigger end of this frustum of a cone, right? It's placed at the bigger end. This end here is smaller than that, and so these two circles are placed at that end. Now, for the third angle projection, the object is placed in the third quadrant, right? And so from where this young man was standing for the first angle projection and where he's standing now, you see that the planes are between him and the object. In the first angle projection, the object was between the young lad and the planes, the principal planes, okay? And that's why the profiles that he was seeing in each of the positions that he took were projected onto the planes at the back. Now, in third angle projection, the planes are between the object and the viewer. Okay, and so what he sees, we assume that those planes are transparent. What he sees are those planes projected to the plane, are the faces projected to the plane between the young lad and the object itself. Okay, so when you open up the quadrant system, you see the third angle projection. Now, with the third angle projection, the right side of your object is drawn, that the profile you see will be drawn on the right side of the orthographic projection drawing. Okay, and then the left side of the object, and that's because whatever you are seeing is projected to a plane between you and the object. So when that opens up, what's on the left stays on the left, what's on the right stays on the right. And then the plan, which is what you see by looking on top of the object, is also rightfully located on top of the front view. All right, and we can see the symbol for third angle projection. The two circles are drawn on the smaller end of the first room, as shown. So that brings us to the end of orthographic projections. I was going to give us some examples, but I think we'll do that when we get to Vision 360. Now let's quickly talk about section views, right? A section view is a type of drawing, engineering drawing, that reveals the internal or hidden features of an object. Okay, and we get to see them by using a cutting plane that goes through the object. Okay, an imaginary cutting plane that goes through the object along the areas that are hidden. Okay, and this is a very typical example. When you look at this object, okay, it has a square-like base that is filleted at the four edges, right? And then there is some sort of a piping system that projects from it. Okay, now we would not have known whether the hole in this pipe goes all the way through or whether it stops somewhere along the length of this shaft of that pipe, or whether it goes all the way down and stops at this face, and all of that. But we are able to know and visualize that internal feature when we apply a section view. So if you look, this is a front section view, this is a plan, and when you look at this symbol, the two circles are drawn at the end where we have the bigger dimension. So this is first angle projection, because what you see on the top goes down. Okay, so we're saying if we get a plane, right, and we slice right from the top down to the bottom, so from that top down to the bottom of this object, then what you will see by looking in this direction, AA, is what has been represented here. Okay, we usually use hatched lines to represent the faces of your section view that have been cut. So this middle part of section AA has not been hatched, okay, because our cutting plane does not actually cut that face, okay, which of course we know from the image that was seen from the isometric projection or orthographic projection that is a curve. Okay. Here are more examples, right, that show sectioning. Okay, and these are a few types of sectioning that we'll look at shortly. But for this looks like a building block. Okay, there is a cutting plane that goes right down through the middle, and then these two arrows indicate your view. If we're going to do that with the plan, now the way we look at this isometric drawing, we would never have known that there is a hole at the bottom. Okay, but in orthographic projection, we are able to see, those features. Now, in this plan view, we will also not be able to tell categorically the depth of this hole, whether it goes through or not. excuse me. Okay, but when we section along this plane, we're able to say that, yeah, that hole that is a part of our sectioning plane goes all the way through to the bottom of the component that we're dealing with, or the feature that we're dealing with. Okay, and then you have another section in there. Just take your time to look at it. This is the plan. That looks like the front elevation. Yes, this is in first angle projection because the plan is under our front elevation, and you see the cutting plane there, and you're looking down, and what you see is this, okay, where the part where the plane has been, has cut is hatched to show that that part has been cut. Okay, and then here you also have two different planes that enable us to see and visualize the features, the hidden features in this single object. Okay, so what are the types of section views that we have? One is full section, and this is a case where you have a single plane, all right, that cuts right through all the objects, okay, and then you are able to see. So in this case, you've got this in isometric view, all right, and this is the cutting plane. If we slice this object right down in the middle where the cutting plane is and look in that direction, what we see has been represented here. Okay, this particular view is the front view, right, without our slicing, without the section, and you see that the dashed lines have been used to show hidden details. Okay, in this front view, you can't tell directly, you can't see these as solid lines, but when you apply this, you see that all these dotted lines have become solid because you can see them with your eyes. And then the hatched and shaded portion is the face where this cutting plane cuts that wedge. Now, do note that even though this plane does go through this particular wedge, it has not been shaded. That's one of the rules of sectioning, that you do not section even if your plane is going to go through a wedge, okay, along its length, because it's assumed it's called the wedge, of course, because it's providing a bridge between this and this, but also you discover that the thickness of it is considerably lesser than the lengths of the sides of the wedge, right? So if you're going to cut, if you're going to have a cutting plane that goes through a wedge like this, you do not hatch it. If, however, we turn this cutting plane through 90 degrees and it cuts that wedge, and we're going to view it from this side, in that case, we show the hatching. It sounded quite ambiguous, but when we come to Fusion 360, we'll create this model and look at what the section view looks like. So full section view is the first, okay? And then there is a second type of section views that we call full section view with offset planes, okay? So if you were going to cut an object right down the middle or at any point where you locate the cutting plane and you may not see certain features, then you offset your plane such that it is able to go through the features that you want to see. Okay. For example, if you look at the isometric view of the sectioned object, you see that there is that plane that comes, okay, and then turns down a little bit so that it can go through the hole and we can see what the hole looks like. Okay, and that's how you show a full section with an offset. Half section is where you have a cutting plane that does not go all the way through the object or goes halfway, and so you are able to see the top half or bottom half of that object without seeing the second half of it, and how you indicate that on the two-dimensional drawing has been indicated here. Okay, and then you have the broken out section view. Okay, this is a case where you are showing just a part. So if you look at this, what do we call this now? I've forgotten the name of it, where you attach other pipes, okay, to that, and it has 1, 2, and 3 openings and or outlets and inlets. Okay, so we just want to see what this particular part of that system looks like. So you have this free curve, and it's not very smooth to show that breakout. Okay, just a part of that to show that, oh, this is what this looks like in the middle without sectioning this side. Rotated section views is a case where you pass a cutting plane and the section view is rotated through 90 degrees, okay, at the point of cutting. So if we look at this is the front, and this is the plan of this component here. If there's a plane that cuts this there, right? If you take this and view it in this direction, what we do with rotated section view is to keep the plan the way it is, but rotate, draw the profile that you would see at the point where you intend to cut it. So for this shape here, that's where you see. And then for this shape, you can see that the section at this end is a perfect circle. The section at this end is an ellipse, okay, some form of ellipse. And then you have an eye-shaped section there, okay, or an eye-shaped piece. Okay, and then here you have removed section, which is quite similar to rotated section, just that you do not leave it at the point of sectioning. With the with the removed section view, you have your section plane, you rotate that view through 90 degrees, right? But you move it away from the body itself. Okay, so you can see the body the way it will look when you look at it, and then you see the sections, of the portions where that plane cuts, removed away from the body itself. All right, so with that brings us to the end of section views and the end of this particular video. Okay, what we are left to deal with is the use of Fusion 360. Okay, that will be the second video to this, where we'll introduce you to the Fusion 360 environment and how to go about drawing basic 2D shapes and profiles, and then the creation of basic 3D models. Okay, so we've looked at the introduction to design thinking, we looked at introduction to engineering graphics, we looked at orthographic projections, sketching, and section views in this video, right? So when we in the second video coming your way, we will look at the use of Fusion 360. Thank you very much for listening.